Now it is 5 p.m. Would someone like to start us off with a homework problem to review?
I'm a bit lost with 2K.
Okie doke. Let me share my screen. Starting from the molecular formula, were you able to determine the molecular formula for this compound based on its exact mass?
There are two pretty good options. I think I chose C8H10O.
That's also what I have. Where did you feel lost on this problem?
Probably just that I didn't work on it that much, but like looking at the IR around the 3000 region, are any of those peaks kind of diagnostic of anything?
I'm not sure that I would say diagnostic. Would someone like to suggest what the peaks in the 3000 region indicated to them?
sp2ch stretch.
Yeah, sp2.
I would agree. Why sp2?
It's above 3,000.
Yep. The reason I wouldn't say diagnostic is because we don't think of alkenes as a functional group the way that something like an alcohol or an alkyne would scream at you in the IR, but because we see CH stretches above 3000 wave numbers, which is to say to the left, we can safely say that those are sp2 stretches that could belong to either an alkene or an alkene as part of an aromatic system. I have both written down. We will eventually, in this coming week's homework, give you NMR spectra, and then you'll be able to determine what the actual structure of this compound is. However, that kind of leads to an interesting point that didn't come up in the jam session last night. What is the unsaturation number for this compound based on the molecular formula? 4. What does an unsaturation number of 4 imply about the structure of the compound, especially one that only has 8 carbons?
Always has double bonds, or
how many double bonds?
3 double bond and a ring.
That's what I would say. You'll find that an unsaturation of 4 or above for small carbon-containing molecules seems to indicate aromatic rings, because 4 is the magic number of the 3 conjugated double bonds, the 4th degree of unsaturation coming from closing up that ring. Benzene ring, exactly. Okay, any remaining questions on 2K?
So in this problem, in terms of looking at the mass spectrum, what are the peaks that we should be focusing on for that particular exact mass?
So we are fortunate in that the molecular ion is visible, in that we can see the 122 exact mass in the mass spectrum. You may have noticed that for some of the problems on this stretch of Silverstein problems, the exact mass or molecular ion peak wasn't always visible by EI mass spectrum, which indicates that the majority of what we're seeing are fragmentation products. And when that's the case, Silverstein includes chemical ionization so that you do at least have the molecular ion peak. Because we have the molecular ion, and because we're not asked to solve the structure yet, the fragmentation products aren't necessarily useful, but would someone like to posit a guess as to what the 94 could be indicating a loss of? I haven't even done the math, so let me check the math on what a mass loss that is.
It's 28, so I thought C2H4, or no, yeah, C2H4.
C2H4. So it would, I tend to think of these visually. So if I had the structure, it might be easy to draw a fragmentation that gives the C2H4. So that would be an ethylene fragment.
Yeah.
Is there anything else that adds up to 28? Or would oxygen be too much?
Carbon monoxide?
Okay. Yeah, good call. So those are the sorts of things that we would be thinking if you were asked to determine what fragments lead to 94. Sometimes structurally, if you are trying to figure out, is it a propyl fragment that is adjacent to the acylium ion I am forming, or is it an ethyl fragment? You go based on number of carbons, and then the mass is useful. But here, without more information, it doesn't tell us much.
And don't we need, sorry to interrupt, a carbonyl for that McLafferty, was it, I think, McLafferty to get the carbon monoxide?
Specifically for the carbonyl McLafferty rearrangement, the retroene, yes, you do need a carbonyl, which you can't have both the aromatic ring and a carbonyl because you don't have the degrees of unsaturation for that. However, James, correct me if I'm wrong, you can have radical retroene reactions that do not start from a carbonyl radical cation. Is that correct?
I think so, yeah. But
Okay.
I think that's really the classic. So I was going to interject that in Silverstein, if you do want to, and really you don't need to go beyond this, but Silverstein does give a nice treatment of at least one case where there's a fragment of 94 and they specifically draw attention to it. It's in section, well, if you go back into the book, and I'll say basically in section, in figure 1.27 and the associated text, you can read about this if you want to. You know, so they mention at least one case that's characteristic on that, and they show a bunch of characteristic aromatic fragmentations.
Thanks, James. Any other questions about K? Other questions from this problem set?
Can you go over the one that has both the monochloro and monobromo compound? I think I
Yes.
understand it. I think I just need a bit more refreshment on how or why we got those fragments.
Sure thing. This problem? Is this number? Okay. And then someone remind me if I forget, someone asked in chat if we could go over problem 4 afterward, the sulfur containing compound. We'll start here. So this question, the crux of this question is you're not told where the halogens are, but chlorine and bromine have distinctive features in mass spec that allow you to place them. Would someone like to not draw out, because maybe not everyone has their document camera set up right now, but would someone like to explain how they arrived at their answer for A?
So for me, I just kind of, I just put like the bromine on the phenyl ring, and then after that, I did the McLafferty rearrangements. So assuming that the bromine is on the phenyl ring, and then the chlorine is like on the end of the alkane chain. After doing the McLafferty arrangements, we see the 198 to 200 MZ. Oh, did I get it backwards? No, wait. No, we're good.
You're good.
After
Yeah,
the,
you're good.
so after the McLafferty rearrangement, the chlorine, so we get C2H3 and chlorine leaving. So then we go from the like M peak to the 198 peak. And then since the 198 and 200 peaks are kind of like a 1-to-1 ratio, that's kind of like support for bromine being on the phenyl ring, because that's the part that's left after the rearrangement.
Exactly. So to summarize, once you identify that a McLafferty rearrangement is likely here, first of all, because you have this carbonyl structure. Second of all, because you can draw the sort of suggestive orientation of the alkyl chain such that you have that hydrogen nearby to the oxygen in order to perform the retro-ene reaction, which is the McLafferty rearrangement mechanism we mentioned in class. What happens next is you have to recognize that of those two fragments, only the charged fragment is the one that you're going to be able to detect by mass spec. And you can tell based on the isotope pattern of this 198 to 200 fragment, like Franco mentioned, because that is 1-to-1, that suggests that that fragment is the bromine containing fragment. And if you know that at the end of a McLafferty rearrangement, you're left with the acylium ion, then this 198, well, there's two ways to go about it, because also the 198 mass is consistent with loss of X as chlorine, carbon H2, carbon H2, carbon H2, or maybe H1 because that one's abstracted. Any questions on A? And Tran, does that explanation for how you're able to identify the position for each of the halogens make sense?
Yeah, it makes sense. Thank you.
Mm-hmm. Part B is not the McLafferty rearrangement. It is a different type of radical fragmentation. Sorry, while I'm finding my problem set, would someone like to explain how they arrived at an answer for B?
I might be wrong, but can I just try?
Yeah, go for it.
So I did a homolytic cleavage of the bond. Can I hold up my paper?
Yeah, go for it.
Okay. This is what I did. Oh, let's see. Can you see that? Oh. So I cleaved this bond right here by the carbonyl. And just did the radical and had it go up and made a triple bond going to the O.
What is the name of that structure?
Oh, geez. I don't know.
The O triple bond with the positive charge is acylium ion.
Okay, I made an acylium ion. Is that right?
Yes, it is. And I'm realizing now that I misspoke when I was talking about the answer to A. You only lose 2 carbon atoms in A. And at this point, it would probably be helpful for me to show my structure for the product of A and B. So the McLafferty rearrangement, because it is a retro-ene reaction, you're left with an alkene as the uncharged radical fragment. Sorry, not radical. Everything's gotten octet there. And then this is not the acylium ion, but simply a charged oxygen radical. Your mechanism, Carissa, for the part B is exactly correct. The mass that you lose is chlorine, 3 carbons, and you form the acylium ion, which is, of course, because it has the positive charge, the one detected, and that has a mass consistent with 183.
Awesome.
And Carissa, can you tell me what the peak is at 155 then, and how that comes about?
Well, I think it's the bromine with the benzene ring. I'm not sure how that, maybe CO2 comes off. I'm not sure.
So yeah, the acylium ion loses CO, so that gets you to the phenyl cation. So that was another mechanism that we saw in class. So yeah,
that's
that
great.
gets you over to there. So further fragmentation of the acylium ion.
Thank you, Carissa. I'm no longer sharing my screen. I'll go back to it. Any remaining questions on this problem? Okay, in that case, we'll move to problem 4, which I believe is additional problem from old midterm exam. Oh, this is what you, okay, yeah, problem 4. This is going to happen a lot where the number doesn't match the number that I've arbitrarily assigned it. This was number 4 on its respective midterm exam. So this is matching metal containing, these are all useful organic catalysts to isotope patterns, and it is matching. So would someone like to suggest how they arrived at a compound for compound A?
So for me, what I try to do, it looked the simplest, right? And I know that phosphorus doesn't have any other isotope. So so going based off only carbon, if there's C44 times 1.1, so the second peak should be roughly half of the first one. So that made me think that maybe it's that binap ligand.
Exactly. So your first observation was that the heteroatom, phosphorus, we can see in the appendix that's attached. Phosphorus only has the one abundant isotope, the one stable abundant isotope, which means all of these features in the mass spectrum are coming simply from the C13 isotopes. But because there are a large number of carbons in your molecule to begin with, it's not unlikely that some amount of those are the 1.1% C13. So yes, I would agree with you. Compound B? Another possible approach to this problem is process of elimination. So if there's another spectrum that spoke to you particularly, you could start at someplace other than B if it seems simpler.
Would compound E be the one containing palladium?
What drove you to that conclusion?
Palladium has a lot of different oxidation states.
So just in terms of language, these wouldn't be oxidation states, but isotopes. The mass is differing based on number of neutrons. But yes, you're correct. This certainly has the largest plurality of different peaks. And if we go to, so this is the tetrakis ligand. If we go to the palladium, no, it should be, oh yeah, there's more than one page of these. Palladium. There's 102, 104, 105, 106, 108, 110. The problem that comes after this, they're all transition state metals. And so you'll notice palladium jumps from 102 directly to 104 with no 103 in between. Can you explain then why in the mass spectrum for the palladium tetrakis, it's not as obvious in this one. Maybe I'll ask you to answer that if we come back to the next metals problem. But for the time being, yes, I'll agree that E is the palladium containing compound. We still have B, C, and D.
So compound C, I caught the osmium tetracide just because it has like the same like abundant like pattern of like osmium where like it starts from like nothing and then like in the ones for like the next two peaks and then like 13, 16, 26 and then like it skips one isotope and then it goes to like 192 and then it has like the largest peak. So that one I put down was like osmium tetraxide.
I agree. Can someone help me with the mass number for osmium? I tried to browse through really quick to find it, but I couldn't find it.
It's on the very last page,
183. Yeah.
Oh, there's 3 of these. I see. Okay.
bottom left of the
There's
very
one.
last page.
Thank you. So V, as you mentioned, you could say that these isotopes are strictly increasing in abundance, which is to say if these are a ladder climbing up, each step is taller than the last one, because the heavier, which is, I think, kind of unique, the heavier isotopes are the more abundant ones. And that is exactly what we observe in the spectrum for compound C. Specifically, it is unique among them in that it's the only one that has that contour. So, correct. Between B and D, they look rather similar at first glance. Would someone like to explain either one?
So for B, I thought that B was iridium because let's see here. So the big peak is like there's like it's like a 2-to-1 ratio with the M-2 peak, I guess, or the peak that's 2 mass units away from it to the left, and that matches the iridium abundances.
How then do you explain these peaks? So this would be, if we call the far left M+0, how do you explain M+1 and M+3?
That's probably just the carbon peaks, or maybe nitrogen too.
Potentially nitrogen, but just because the relative abundance of carbon-13 is greater than nitrogen, I think, is it nitrogen 16 to 15? Or 15 to 14?
15 and 14. 15 is 0.38% and 14 is 99.62.
Okay, right. More carbons. Carbon has the higher isotopic abundance of the heavy isotope. So yes, I think those can be explained by carbon, which leaves boron for compound D. And if we look at the isotopic abundance for boron, M would be boron 10, which is roughly 20 to 80 to the 0 to M+1. But in the boron spectrum, we see that there is an M+2. Same explanation. This boron containing compound has a good number of carbons that could contribute C13 to M+1. Any other questions? Oh yeah, go ahead.
So in the boron cases, it's just kind of like a coincidence that the carbon peak is almost the same as like the boron, like the boron 10 peak.
I am slow to label any interesting phenomenon in chemistry a coincidence these days, but yes, I do think it's coincidental. It does look cool though. Okay, other questions about this problem? Back to the full problem set.
Can you go over number 4 on that packet?
Yes.
The one with like the peaks with like many isotopes.
Ah, I believe this is the sulfur-containing compound that I mentioned earlier. This problem?
Yes.
Okay, I'm glad you asked because this is probably my favorite in the problem set. This one is especially useful to understand correctly. So the neutral molecular formula, we're told, has carbons, bromines, nitrogens, oxygens, sulfur. Notably, we're not given the number of hydrogens because problem B is asking us to figure out, based on information we have, what the number of hydrogens is. But the first problem, and I'd like for someone to explain this, explain the spacing of the peaks. So first of all, what is the spacing of the peaks? And then how do you explain why the spacing is what it is? This is a rather large isotope pattern. Could someone explain answer A?
I can do it, I think. So the spacing between those peaks are around 0.3, which makes us think that it's going to be a third of like the actual like supposed normal distance of m over z. So that means that if the distance is like around 0.3, it means that z is 3, not because it's 0.3, it's 3, but 0.3 as in like 1/3. And then that would make z has a charge of 3 for this section in particular. So that's why it's, yeah, that's the spacing. I think, I hope that explains well.
That is the correct explanation. For anyone who didn't follow, the takeaway is this is only a very small part of a larger spectrum. This only goes from 1236 to 1244, when in reality, because of fragmentation, mass spectra for large molecules could be much larger than that. And even though we don't have the number of hydrogens, if you were to add up the mass just from the carbons, bromines, nitrogens, oxygens, and sulfurs, that already is heavier than 1244. So we know that none of these peaks in this spectral pattern are the molecular ion. We're looking at something that is more charged than just the M with a single charge. M over Z, if you add a single proton to a compound, Z is 1. So when we're looking at the detected mass of M over Z, what the mass detector is actually showing us the number of, usually we're looking at the molecular ion. But in this case, Z is not equal to 1, it is equal to 3, which means we are looking at masses that are a third of the actual mass of whatever compound is hitting the detector. The way that we know that is the spacing of these peaks. So the difference between 1239.2 to 1239.5 to 1239.8 and so on is roughly 0.3 or 0.3 repeating or 1/3. If you were to zoom out and extend this mass spectrum over to, I don't have the paper in front of me, but part of this problem is calculating the overall mass of this molecule. If you were to extend it out to see the M+1 peak, the spacing of that isotope pattern would instead have a spacing of 1. And then in between this M over Z is equal to, or sorry, Z is equal to 3 pattern and the Z is equal to 1 pattern, you would also have another pattern in between those two where the spacing would be equal to 2. And then depending on how many positive charges your macromolecule can handle, you could get a Z equals 4 pattern, a Z equals 5 pattern, and in each of those cases, the spacing between peaks would be 1 over whatever it is. So the very short answer to problem A is the spacing of the peaks is 1 over Z, which is a third. Z is equal to the net charge on the molecular ion, which is 3. I spent a lot of time on that explanation because I think it's important that people understand this. And if you take a mass spec of your own, especially on the ESI instrument in the mass spec facility, you'll see this phenomenon for yourself. Does anyone have a question before we move on to part B? Okay. B is asking, using the tables of isotope weights and isotopic abundances, estimate how many hydrogens there are in the molecular ion. Would someone like to suggest their answer for B and give an explanation?
So for this one, I got 210 hydrogens in the molecular ion. So the way I did this was I took the leftmost peak that we got, the 1239.2, and then I chose that one because that one would be like that one would be the peak where all the elements are like the lowest mass. So those are that peak has the elements where all of the masses are like the lowest they can be. So then we can like assume that it's like carbon 12, bromine 79, et cetera, et cetera. And then that's important because once we do that, I did like 168 times 12, 78.91 times 2, whatever. So whatever the smallest mass was for each element, I multiplied that by how many atoms there were. And then I got 3,505.6 for that one. And actually, I kind of jumped around. So the leftmost peak, right? If we multiply that by 3, that'll give like the total mass of the molecular ion. And then once you multiply like all of the masses times like the number of atoms in the formula that they gave us, we got 3,505.6, and then 1239.2 times 3 is 3,717.6, and then 1,239.2 times 3, that number includes the hydrogens. So then to get the number of hydrogens, I took 3,717.6 minus 3,505.6, and then I got 212. However, we still need to divide by the mass of hydrogen in order to get the actual number of hydrogens. So after that, I got about 212 hydrogens with rounding.
You mean 210?
Or 210, yes. 210 hydrogens right after rounding.
Exactly. So does everyone understand why we need to divide by the exact mass of a hydrogen atom? Are there any questions about that?
Can I can I just fix that and resubmit? I'm sorry.
Yeah. Different color pen. If anyone is annotating their homework with a different color pen, I would much rather see that you arrived at the correct answer after attending discussion or the jam session than see that you still don't have the right answer. We want everyone to get the right answer. Okay, Franco, thank you. Excellent explanation for B. So in the molecular ion, which just to remind everyone, mass spec only detects charged species, we have 210 hydrogens in the charged molecular ion. And again, this isotope pattern corresponds to a +3 charge. So C is now asking, based on the number of hydrogens in B, what is the molecular formula of the neutral molecule? So can someone briefly explain the difference between B and C?
So isn't it the case that this technique tacks on protons as part of its mechanism or mode of detecting the charge? So if we've got a +3 charge, and if the way you get that is by tacking on protons, then the number 210 that we just calculated contains those 3 additional protons. So we have to back those out to get down to the neutral molecule. So we would subtract 3 from 210 to get 207.
Precisely. Thank you, Chris. Question D is saying, thank you for jumping through all of the hoops to perform all of the math and arrive at 207 hydrogens. However, that's not quite correct. Explain why it is not 207. Would someone like to explain their answer for D?
If you have 207 hydrogens, the like unsaturation number comes out to not be a whole integer, and so you have to like change it to 206 or like 208, which I think the unsaturation number for 206 photons comes out to be 84, and 208 photons, the unsaturation numbers comes out to be 83.
Exactly. Thank you, V. You can't have a non-integer degrees of unsaturation. It's fine to have 0, but if you have a non-integer degrees of unsaturation, you may have neglected a hydrogen to count somewhere. It may be a charged species for which degrees of unsaturation that formula no longer correctly applies. So an even number of hydrogens in this case gives a whole number degrees of unsaturation. Exactly. And then finally, what are the two main isotopomers that contribute to the peak at mass over Z 1239.8? And if we look back, 1239.8 is not the M or M+1, but the M+2 peak. So where are those extra 2 atomic mass units coming from? And there are multiple answers for this. Some are better than others.
I guess one could be if you have one bromine 81, so 79, so that's +2. And since we have a lot of carbons, it's possible that we can have 2 carbon 13, so that's also +2.
That's exactly what I would say. Bromine, it's easy to explain away an extra bromine 81 because 50% of bromine, roughly, is that extra 2 mass units. And in a large molecule that has, I believe, 168 carbons, it's not unusual to think that 1 or even 2 of those are the 1.1% of carbon 13. Thank you, Emily. Okay, again, this problem is very important to have a good grasp on in terms of your understanding, because being able to recognize the charge state of a fragment that you're looking at based on the spacing between the peaks, it's important to understand why that's the case. So are there any remaining questions about this? Was problem number 4. Okay, someone asked me in chat if we can go over problem 7, part B, but we may just start at A for completeness' sake. Iotoxin. Whenever I see a molecule that looks like this, I always describe it as coming from some esoteric sea snail. A professor of mine in undergrad described it that way. So, of note, this was detected in the negative ion mode, and before adding or subtracting any atoms, just the toxin itself already contains sodiums, which is useful to know. So the first question is asking, what is the mass to charge ratio of so this is the isotopomer with no unusual atoms. This is all the most abundant, so no C13s, of the ion that is missing a sodium. So because this is the negative ion mode, loss of a sodium would then be detected as a negative ion. So would someone like to explain their answer to A?
So I took all of the masses and I added them together. And then since the M to Z ratio is mass over charge, the charge is -1, but the Z value is an absolute value. So I just divided the mass I got by 1, and I got an M to Z ratio of 3400.59.
Exactly. If you got a number other than 3,400 or 3,400 and some decimal, double check your math. During the jam session last night, we arrived at different numbers, but upon redoing them, all arrived at 3,400. We're helped out by the fact that all of the carbons are C12 in this particular isotopomer. But again, if you got something other than 3,400, check your math. What is the isotopic composition of the predominant isotopomer of this ion? And I will ask what people said, and then I will explain how I arrived at a conclusion, and then I might toss it over to James for an explanation of some of the more acute statistics involved.
So I was using the molecular formula finder that we were provided with, and I said that one of the isotopomers was carbon 13, just one of them. And then for the question where it said if you're uncertain among a couple possibilities, explain below, I saw that there was a peak to the right of the one carbon 13 peak. And I said that another possibility could be that there's two carbon 13s in this molecule, but it was more likely that there was one carbon 13.
So when you say you used the molecular formula finder, do you mean you typed in the molecular formula in order to see the isotopic distribution?
Yes.
Okay. In case anyone in the discussion was unaware of this function, in addition to the tab that allows you to type in an exact mass and it will give you a formula, you can type in a formula and it will give you an isotopic distribution that includes all of the statistics of relative abundances. And so, Anastasia, what you're mentioning is that this most abundant ion appears to be the M+1.
Yes.
And then you said that an extra C13 was the most likely way to arrive at that?
Yes.
I would agree with you. Are there, so I think that hydrogen, oxygen, sulfur, sodium does not, but everything other than sodium, in theory, you could end up with an M+1, but not only do you have fewer oxygens and sulfurs than you do carbons, but the relative abundances of those heavy isotopes are so much dramatically smaller than the 1.1% of carbon is, that I'm led to believe that the most likely way of getting that extra mass unit would be from a single carbon 13. James, would you like to comment at all on the actual statistics of doing this math?
So I guess what I'd say is I'm looking for sort of calibrated intuition rather than doing the statistics. And I remember back from a long time ago in doing statistics, certainly one way of doing it is, okay, what's the likelihood that one carbon is C13, and, or to put it another way, that they're all but one is C12. But honestly, when we were dealing with small molecules, we basically said, okay, methane, 1.1%, ethane, 2.2%. You get up to, C30, it's about a third. If you get up to about C90, C92, then it goes to about 1:1. And then when you get about twice as high, it tends to be, now you're up at 2 C13s. And if you don't have the intuition yet, you can. So let me share my screen.
Oh, you're muted, I think.
Dr. Nowick, I think you're muted right now.
Let me unmute myself and then again share my screen. So, you know, by now we should be calibrated that if you have a molecule with 2 carbons, you'll get a little m+1 peak. If you have a molecule with 10 carbons, it's going to be bigger, about 10%. For many organic molecules that are sort of mid-sized, you're going to see an appreciable m+1 peak and also start to see a significant m+2 peak. By the time you get up to about C90 or C92, right now, your m+1 is equal to m+. And by the time you're up to maybe, I don't know, 170 or 180, now you're going to basically be up to, you know, okay, 190. Now you're going to be up to the m+2 being the biggest. And that sort of makes sense if you have something that's 1%. So for a giant molecule, you know, you're going to see a substantial m+2 peak from 2 carbon 13s. If you're worried about the other stuff in the molecule and you say, well, what about hydrogens? Let's suppose I had a molecule with 256 hydrogens. Can we barely, you know, we could just barely see deuterium, but it's not going to do much of anything. A molecule with 68 oxygens, you know, barely registers for anything for your O18 or O17 components. Couple of sulfurs will do a little bit, as we talked about in class, but the big thing is going to be the carbon isotopes and of course halogens and so forth by the time you're dealing with molecules with lots of carbon. So I guess the other thing I'd say, this was an exam problem. It was meant to be sort of guiding people through thought processes. I didn't actually care if people answered 1 carbon 13 or 2 carbon 13s, as long as they got the idea. There's a lot of molecules that have at least 1 C13 by the time you're up to 168. So that was my goal here on this problem, was basically to guide people through. We had never done a negative ion mode problem, and I wanted to guide people through the thought processes and then build on the thought processes we had used in that earlier problem with the 160, whatever it was, 4 carbons and or 168 carbons and the sulfur and bromines.
So there was everyone. Can you see my PDF now?
Mm-hmm.
Okay. So we were on B. C now is asking, what's the formula of the cation that you would expect to observe in the positive ion ESI mass spectrum of myotoxin? Someone like to suggest? Based solely on my own research and what I've observed, I would accept more than one answer for this problem.
Me too.
So you could just take the original formula and either stick a proton in H, add an extra H, or extra sodium. I did an extra H because it's just easier. Just add 1 to everything.
Exactly. Either a proton or a sodium or a potassium, you sometimes observe in MALDI, I certainly do, will give you the charge necessary for it to be detected in the positive ion mode. And all you have to do is, in your molecular formula, account for the fact that you either have an additional hydrogen, which would be 257, or an additional sodium, which would be 3 total, giving you that positive charge. The peptides I make, the sodium peak is actually taller than the hydrogen peak, indicating that it prefers to fly as the sodium cation rather than the hydrogen cation or proton cation. But again, I agree, the math's easier if you're only adding one mass instead of the 23 from sodium. And then for that specific cation, what is the mass to charge ratio?
I got 24.59.
Exactly. And it's just the mass of the original molecular formula. And then it specifically tells you the isotopomer that has all of the most abundant forms of each of those isotopes plus 1.00783 from the extra hydrogen. And if you had suggested instead sodium, you would add 22.9. If you had suggested potassium, it's not even on here, but that's 39. Right, James?
Yeah.
Okay.
Yeah, it's 39. And the one thing I'll comment that's on all of these problems is in the text, I use the term isotopomer, but the correct term is isotopolog. So we will keep that in mind. Maybe one of these days we'll figure out whether we can correct the PDFs.
Right now, it is 5:51. I am more than happy to stay here and continue to answer questions. And I know that one person asked if I could demo Maestro because they were having trouble using Maestro, and I'd be happy to do that as part of this discussion if James is willing to host the video and continue recording. But if you do not have any further questions, this is the time that discussion ends. Before you leave, extra credit for before everyone leaves, there's one note about this upcoming week's homework. Over the weekend, I was supposed to go to the NMR facility in Natural Sciences 1 and record myself taking a proton NMR of strychnine. For any of you who have not done NMR before or have simply not seen our facilities because they've been shut down for months now, I did not have an opportunity to do that because the 400 megahertz was offline over the weekend. I will have that done and the video updated to Canvas before Friday evening at the very latest. I plan to do it before then. So you'll notice the last part of the homework, it says link, but there's no link there. It's forthcoming. And if you get to it before me, send me an email saying, James, I finished everything. Where's my video? And I'll prioritize it. Other than that, I'll see you all for lecture on Wednesday. Are there any other questions about this problem set that people would like to go over?
James, you said it's not for this homework, right? The NMR, that's from next homework.
Correct, sorry, following week. So the one that as soon as I'm done with this, I'm gonna publish homework 3, but it doesn't yet have everything it needs.
Sounds good, thank you.
Sure thing. Oh, I'm still sharing. If there are no other questions about problems from this problem set, I'm going to quickly demo the first part of the modeling exercise in Maestro. That's strange.
Do you need to be VPNing in, James?
I don't because I'm on the housing Wi-Fi, that's right.
Wait, I'm also on the housing Wi-Fi and I had to VPN and it didn't work if I didn't.
Which housing are you living in?
Campus Village, right next to NatSci.
Should work.
You're
on Skynet?
Yeah, UCI ResNet, residential net.
Oh, ResNet.
Yeah.
And what are you on, James?
I don't even remember the name. I have a router of my own.
Okay.
ResNet.
In any case, as long as you're able to access it using the VPN, it's just a matter of inconvenience. Campus Village, because undergraduates also live there, their internet might have different permissions than the graduate student housing. That's the only rationalization I can give.
Yeah.
I think undergraduates still live there.
Yep, probably, not sure.
Okay, so using the Maestro 3D Builder, construct morphine in stages. I realize that I'm on a rather high resolution display right now. So if you on your laptop or computer can't see the names of the buttons I'm clicking, let me know. Yeah, what's up, James?
Can you share?
I'm not sharing my screen. Ta-da, okay. Now we're looking at Maestro. Sorry about that. Of course you couldn't see what I was clicking on. Okay, this is the build. It is a wrench and a hammer. And now we enter into the Maestro lagging stage of completing the homework, because sometimes it takes a moment for the builder tool to pop up for me. I might need to minimize, maybe it's opened on a different monitor screen. Okay, I'm gonna try something. Sometimes having more than one display is more trouble than it's worth. I'm gonna disconnect my external monitors, bring everything to the same window. Sometimes that helps. Yeah, okay, I have the builder now. So I'm going to resume sharing my screen. Is everyone able to see Maestro?
Yes.
Okay, thank you, James. This is the window that opened up when I clicked build, and now that it's not buried behind my multiple tabs on multiple screens, you can pull it to wherever. I think I'll pull it here just so that people can see it the easiest. So the PDF is first asking, oops, I did not at all mean to open Discord. Whoops. Okay. So we're starting with a cyclohexane with an equatorial methyl. So add fragments, and there is a cyclohexane fragment. If there's nothing selected and the workspace is empty, clicking a fragment will simply populate the workspace with that fragment. And you can see the spinning icon indicating that Maestro is running slowly. Oh, and it's not responding either. This happens to me, it says not responding, it just takes a moment. Although I will say this is longer than I'm used to. Okay, there we go. And the builder's back, that's good. So now, confusingly, the 3-button mouse commands are slightly different for Maestro than they are for PyMol. And I'll learn them right now. So it appears that left mouse button is select, middle mouse button is rotate, and I will rotate it into the conformation that mimics that of the PDF, and right mouse button is translate across the screen. If I scroll, that changes the view, which is intuitive. PyMol doesn't do it like that, but I prefer when scroll changes the view. In order to change this hydrogen to an equatorial methyl, simply select it and change it to a carbon atom. This just changes whatever selected atom to a particular atom of that type. So now I've constructed the equatorial methyl. The next step is, let's go ahead and change this to a nitrogen in the exact same way. You'll notice that it automatically got rid of hydrogen. It's possible that it leaves hydrogen behind, in which case this would be an ammonium. And I believe in that case, the color of the nitrogen changes slightly to reflect that it's positively charged. Also, James, could you help me keep track of the chat? I see that someone may have said something in the chat, but I can't read it right now.
Can I ask a quick question?
Yeah, go for it.
So if you, did you ring flip it? I might have missed that. You might have said that already.
The way that I did that was using the middle mouse button. You can rotate your view. So when it originally dropped the cyclohexane, it may on your display have dropped it like this, where it looks like a hexagon. You'll have to hold the middle mouse button or the scroll wheel drag it around, and then here it's sort of backwards and upside down. So if you just do small circular patterns, it will eventually sort of get to a view that looks similar to the two-dimensional representation on the problem set. Does that answer your question?
Yes, thank you.
Okay. So now I want to add a phenyl fragment to this axial position. You can add fragments in the same way that you can change atoms. So right now I have this axial hydrogen selected. I'm just going to change it to a phenyl fragment because that saves me the clicks of trying to change each of those individual atoms to a carbon and then change all of the bond orders and such. This axial hydrogen has to be a carbon atom. And now I'm going to create a bond between these two atoms, but if I just click, it changes which one is highlighted. So on Mac, I'm sure it's Command, and on PC, it's Control. If you hold Control and select more than one atom, it will keep them both selected. Now I can create a bond between these two atoms, and this is great. However, if I change my view, you can see that unless it's viewed at this angle, that bond does not really make spatial sense. It's far too long. You can minimize structures by selecting all atoms using Control A or Command A just meaning all. And I could click minimize selected atoms. This is similar to cleaning in Pymol. However, I'm not going to do that because it takes a long time on my computer. You're effectively doing a minimization, but as long as you can keep the atoms straight in your head, even though this bond is far too long, it's a time saver to not do it right now. So now I need to add an additional, so this is going to end up looking like a decalin. So I need to add 4 carbons to the right side of this molecule. Yes.
Can you slow down a little bit?
Sure thing. Sorry.
Yes, because I'm trying to follow you with my graphic too. So thank you.
Yes, no problem. Let me know. Go ahead.
Sorry, I didn't mean to interrupt you. Could you repeat how you selected 2 atoms at the same time?
Exactly. Are you on Mac or PC?
I'm on a Mac.
Okay. Try holding, I believe it's Command, and clicking on the atom on the phenyl ring and the carbon atom, the axial carbon on your cyclohexane. Are both of them selected if you hold Command?
Thank you.
Okay, so it did work. Good.
And I will also be making the video of today's discussion section available on the website. So if you
great.
needing to go back, it should be available probably by the end of this evening.
Sounds good. Okay, so Han, let me know as soon as you have this structure.
Yes, my program just stopped responding, so I have to open the back again. But you can keep going, so everyone don't have to wait. And then I'll just go back and watch the videos.
Are you sure?
Yeah.
Okay.
Thank you.
So now I know that I want to change both of these hydrogens to carbon. So I'm just going to select both of them at the same time, change them both to carbon. And then I need to, again, change these 2 hydrogens to carbons. And now you'll notice that because I changed those atoms, they remain selected. I'm just going to create a bond between them. And very quickly, I've made the 4 carbons to construct the rest of this part of the ring. Next, we need to change the bond order here. You can select bonds in the exact same way that you select atoms. And rather than creating a new bond, I'm simply going to increase the bond order. And again, Maestro very intelligently, you could say, recognizes that I've increased the bond order of each of these carbons, which means they had to decrease the number of hydrogens on those carbons. Okay. Next up is oxygens. All right. We'll take a quick pause for people who are following along.
I have a question. So you can move you can rotate it with your middle button, but how do you, well, I think like mine's like slanted and I can move it, but I can't get it straight. Is there another way to rotate?
Off the top of my head, I don't know of any shortcuts other than the mouse. If you email me, I'll look through the documentation. I'm sure that there's a way up one of these, because in PyMol, there's a command that centers your view that's really helpful called orient, but I don't know of a comparable command in Maestro.
Okay, thanks.
The most trivial of these three oxygens to change are the one on the phenyl ring and the one that's an axial proton. So I'm just going to, for convenience, select both of them since I'm changing them to the same atom type. You could do it one at a time, or you could do them both at the same time. And then finally, we're bridging this ring to this ring via an ester linkage, which means one of these two hydrogens has to be changed to an oxygen. I'm going to choose this one. And now there needs to be a bond between that new oxygen and this carbon atom. And I'm going to create the bond there. You'll see that all of the bond angles and bond lengths are pretty messed up as a result of me choosing to do it in that order. But the next step is now to clean up the structure as needed during the building process using minimize and all atoms. So now that we've done all of that, I'm going to select all atoms, choose minimize, and then sign off for about a minute while my computer chugs its way through this minimization. Are there any tangential questions at this point in time? I'm not sure if I'm even still in the Zoom call because sometimes my computer shuts down other applications while it's working so hard on this one.
Do you know why Maestro is so heavy on the computer?
Molecular dynamics simulations and even just modeling in terms of sterics, not taking into account molecular orbital theory or anything higher level, is not a trivial operation for a computer that isn't dedicated to that sort of thing. And I think it's just that consumer laptops these days aren't built with these operations in mind. It takes a lot of processing power because basically what it's doing right now is if you were running a molecular conformation search, it would be doing a Monte Carlo. Oh, hey, check that out. Okay. So that looks good. I'm going to continue what I was saying, though. You are either doing a Monte Carlo sampling where you're making small changes to bond angles, bond lengths, sometimes breaking bonds and remaking them, and then doing an energy calculation every single time, sometimes for as many as 2,500 iterations, which is what is in next week's homework. Or even if you're just doing something like this, you're doing calculations to optimize bond lengths and angles based on the whole molecule around it. So not trivial. I wish my computer did it a little faster, but I like my laptop. Okay, all of these bond lengths and angles look correct, and it's not part of this warm-up exercise, but in exercise 1, you are asked to perform an actual got to keep scrolling, an actual minimization in order to determine energies. Would anyone like me to walk through this exercise as well? Who do we still have present in the call?
Yes, please.
Okay, great. Then I will go back to sharing my screen. So the first part of this exercise, please read it because you'll need it in order to do the math. But brief summary, I didn't practice this. Lots of different calculations go into determining the energy of a molecule computationally. Different bond lengths and angles lead to different types of steric strain and other types of increasing energy. And so a conformational search can help you find the most stable conformation of a molecule. Maestro is good at determining the differences between conformations, but not necessarily changes not related to simple bond rotations. So these are examples of stabilization through resonance, and Maestro, without the correct electronic simulation package, wouldn't be able to tell you that energy difference accurately. You can use the Boltzmann distribution in order to determine the relative abundance of a particular conformer based on its energy. And logically, the more stable of two conformers is more abundant, but you still have a small amount of the less stable conformer. An example is given of anti-butane and gauche butane. And finally, the exercise. So first, we need to construct three different one of two isomers of this decalone, and then two different conformers of the cis decalone. I'm going to start with the trans. So this is cyclohexane, this carbon. Okay. Let's see if I can remember it without having to go back. You can clear the workspace, clear workspace. Goodbye, morphine. We're on to bigger and better molecules, well, smaller ones.
Should we save our morphine?
I don't believe we're using morphine in Maestro for any future problems. Oh, it might be exercise 2. Yes, definitely save it. I think that this week's homework actually has you doing conformational searching of morphine. So yes, thank you for asking that. That's a great idea. Okay, I already forgot what it looks like. So we're adding, okay, so it's a decalin. I believe that if I highlight these two atoms and I click this fragment, yes, it will create a decalin. It's a similar shortcut to the one in ChemDraw. In order to make this into a ketone, I can change this atom into an oxygen and then change the bond order of that new carbon-oxygen bond to be 2. Maestro is smart and will automatically get rid of the unnecessary hydrogen. And then finally, I'm making this into a carbon. At this point, we are actually going to perform a minimization. I have minimize added to my taskbar because I've used it before, but the way to navigate it if you are using Maestro for the first time would be MacroModel is a software package for the Maestro user interface. I'm going to close the builder. So tasks, browse. Here, an example of packages I do not have installed, but one that I do have installed is MacroModel. Now, if I click on MacroModel, there's a star next to minimization. And if I click the star, it puts it on my taskbar. And now if I open minimization, yep, I'm just waiting for it to open. Okay. Once we do, okay. And there is an individual in my housing complex who around 6 p.m. every day, I believe he is a professionally trained opera singer. He practices. If you can hear what sounds like opera singing in the background, that's exactly what that is. Just so you know. Okay, we've opened the minimization window. Select MMFF under force field. You can read about that force field earlier in the, did I accidentally uncheck this? Oh no, I didn't mean to. Can someone tell me who's using Maestro right now whether this option begins checked or unchecked? I accidentally clicked on it. I don't think it matters because we don't have metals, so I'm going to leave it checked and hopefully it doesn't change the results.
I don't think it's going to matter.
Okay, I didn't think so either. So force field MMFF, none under solvent. Give the job the name trans and select run. I already have one named trans, so when I choose to run this, it will ask if I want to delete them, and sure, it's going to end up the same. So now Maestro will take a moment to initialize the run. When this starts making a spinning motion, you will know that the run has started. Also, I believe jobs, underneath jobs. Okay, so trans started. Now we wait. Running. Once this is complete, we'll open up the job table. But in the meantime, my computer will freeze and we will wait. Okay. Now I should be able to, okay, so it says your job has been incorporated. My understanding of what that means, view in project. Yes, when it says incorporated, it means that you can now use the minimized version of whatever it is you just ran a minimization on. So you'll remember that before the bond angle of the carbonyl was incorrect because I changed it from an axial hydrogen, but because I chose to incorporate it, now we're looking at the minimized structure. If I go to the job table, we can see the energy in kilojoules per mole of this minimized structure. And let me quickly corroborate that that is what I have from my previous notes. I didn't write it down. Bummer. I guess I can write it down now. 93 sounds correct.
That's what I got.
93.350. Great. So we could continue this for the cis isomer and each conformer of the cis isomer, but it is the exact same process. So I don't think there's a reason for me to demonstrate it, but if someone has a remaining question from Maestro, I can still answer it.